Okay, so this is the outline of my talk. It's going to appear a little bit backwards. I won't tell you how we actually make these circuits until the end, because if I show you a bunch of circuit diagrams, you won't be interested. But if I show you all of the cool things we can do with them in the beginning, I think that will pique your interest a little more. So I'll start with some of the limitations of passive RF structures, metamaterials, small antennas, and then I'll talk about the basics of how we build these structures that we call non-Foster circuits, negative capacitors and negative inductors, and then some of the things we can do with them. Matching small antennas to exceed the Wheeler-Chu limit, for example, broadband parasitic arrays, superluminal structures for broadband antennas, cloaking, and other applications. And then at the end, I'll show you how we actually make them and some of our preliminary measured results. So first, let's talk about limitations on some of the popular RF structures. Well, many of you are familiar with this concept of metamaterials. Of course, that's a new term for the current evolution of a field that's been around for a long time. In the old days, we called them artificial dielectrics. We could make permittivities that we couldn't otherwise achieve by building in metal particles into a dielectric matrix, for example. Now we can also play with the permeability. So we can make effective media that have effective mu or effective epsilon that's almost anything we want, including high values, even negative values, or near zero values. Of course, they generally rely on resonance. So these permeability curves that you'll see are often a shape sort of like this. And so you can get negative permeabilities. They're often narrow band, maybe on the order of 10% or so for a lot of the structures. One of the other issues that I have with this field is a lot of the focus is on 3D structures. And there's a lot of interesting things you can do with them. Of course, they're somewhat difficult to build. This is one of the popular examples. It's not only the difficulty in building them, but a practical difficulty in applying them. For example, one of the popular applications these days is cloaking, making waves bend around solid objects. I'm sure you've all seen this in the news and in various papers. However, they often require a volumetric or a very thick coating around the object to be cloaked. I think a more practical approach is a surface coating, if that can be developed, surface only. And in fact, one of the things people don't realize about this whole business of cloaking is we often don't care about all directions. Sure, it would be cool to have a coating you could put around something that would make it appear invisible to all directions. But for real applications, we know what direction we're flying, we know where the radars are, and we know what direction we'd like to cloak. So this is a good goal, although you can make many more practical things by applying simple surface coatings. And I'll show you, I'm working on passive structures for this, but in this talk I'll also show you active structures. So this is where a lot of my research is going, if I could summarize for you. If we look at electronics, if we were stuck with just resistors, capacitors, and inductors, we couldn't build any of the things that we have today, computers, radios, all of the RF circuits, everything you build with active electronics. But with transistors, with diodes, feedback circuits, etc., you can do all sorts of amazing things. So if you apply that same idea to RF structures, metamaterials, antennas, whatever you like, you can see a similar parallel. The current approach using LC resonance, I would say, is similar to what we'd have if electronics were just resistors, capacitors, and inductors. However, if we have all of these other devices, well, we can include amplification. We can get broader bandwidth than we could otherwise get with simply passive structures, as I'll show you later. And we can do all kinds of things that would just be impossible with passive metamaterials or passive antennas, superluminal propagation. I'll show you various things we can do with absorption that I won't talk about in this talk. So, first of all, what are these so-called non-Foster circuits? Basically, the simplest way to understand them is they behave as negative capacitors or negative inductors. This is a figure taken from Foster's original paper in the Bell System Technical Journal back in the 20s. And so basically he showed that the derivative of the reactance of any passive lossless circuit or network is always positive with frequency. So, for example, an inductor has a reactance of omega L, so it's a positive slope with frequency. A capacitor is negative 1 over omega C, so negative but also positive slope with frequency. So what would be a negative inductor or a negative capacitor? Well, it would be just the same thing, but this would be a straight line with a negative slope, or a negative capacitor would be the same curve but just flipped upside down. Now, Foster's theorem applies to more complex structures. So, for example, a series resonant circuit, that looks a lot like many small antennas that you might build. And so the reactance can be 0 at exactly one frequency, and you can see the reactance goes very high, positive or negative, at other frequencies. And so the antenna is really only efficient right around that one spot. You can also see, for example, this parallel resonant LC circuit. You can, again, get positive or negative values, but the slope is always positive with frequency. Now, if you add in a little loss, of course, this curve doesn't go up to infinity and come back. You can get a negative slope by adding loss, whether that's radiative loss or resistive loss or whatever. Now, thinking about these in terms of the Smith chart, as many of us in RF design like to do, notice an inductor is on the top half going in the clockwise direction around the Smith chart, a capacitor also going in the clockwise direction on the bottom half. So a negative capacitor would just be the mirror image of that going in the counterclockwise direction, similarly for a negative inductor. Now, what about that lossy parallel resonant LC circuit where we get that little region in between these two curves where we get a negative slope? Well, that would be a loop around this Smith chart. The LC circuit will give you a loop. And if it's lossy, you could imagine a loop in a portion of the Smith chart where over some frequency range, it appears to be going counterclockwise. Of course, the loop is really going generally in the clockwise direction, but that small piece could appear to be going counterclockwise if you don't look at other frequencies. So let's talk about the simplest application, actually not the oldest application, but currently the most popular one for these circuits is broadband small antennas. Wheeler and Chu came up with, back in the 40s, the relationship between antenna bandwidth and efficiency versus electrical size. So the Wheeler-Chu limit says you can always make an antenna smaller and smaller at any frequency you want. You can have a UHF antenna that fits in your pocket, but the bandwidth is going to be reduced in relation to the electrical size of the antenna. So K is 2 pi over wavelength. A is the radius of a sphere that surrounds the antenna. And you'll see many claims out there of antennas that appear to contradict this limit. Companies are selling so-called chip antennas and things like that where it looks like this 1 or 2 gigahertz antenna is just a little tiny chip. In fact, that's really just a matching structure for the rest of the antenna that you have to provide. And so if you count the volume correctly, which means the whole antenna, including any ground plane, if that ground is electrically small, then none of the antennas violate this Wheeler-Chu limit. Now, the bandwidth relates to that Q either if you're talking about a matched antenna through this equation here, or an unmatched antenna. If you look at the Smith chart here, the matched antenna is crossing through the origin of the Smith chart. The unmatched antenna sort of traverses around the origin. You can do a little bit better, ultimately limited by the Bode-Fano limit that tells you what bandwidth you can achieve for a given Q and a given reflection coefficient. So some of my students and I did a study of this. We actually looked at every single small antenna paper published in the IEEE transactions on antennas and propagation, going back to the beginning. We even looked at the IRE transactions before that and took anything that came up under the search term small antenna that included measured data and just plotted them all out here. And you can see none of them are beating the Wheeler-Chu limit. This one would appear to, but remember what I mentioned before about unmatched antennas. That one's not matched. So if we included the Bode-Fano limit, there would be another curve that's slightly higher. Almost all of these are matched, though, so we went with the matched curves. And you notice a few things. One of them is, as I just mentioned, none of them are beating the limit. Another thing is these little plus signs are the metamaterial-based antennas, not doing particularly well compared to just good, classic, well-engineered conventional designs. Why is that? Well, these are using resonance structures, and one of the things that Wheeler describes in his original paper is if you confine the energy in the antenna to a subset of the real antenna volume, you're going to get reduced performance, and so this is verifying that. So, okay, what can we do with non-Foster circuits, negative capacitors or negative inductors? Again, I haven't told you yet how we'll build them, but I'm trying to sort of pique your interest. These are some relatively recent measurements from Steve Sussman-Fort and also Steve Stearns at Northrop. And it turns out it's not that easy to prove that you're beating the Wheeler-Chu limit, because you could always make a broadband antenna, just add a lot of loss, right? You can secretly put a 50 ohm load inside your antenna and it'll appear perfectly matched over as broad a bandwidth as you want. So the correct way to measure performance is improvement in signal-to-noise ratio over bandwidth. In fact, if I were to go back, this is really bandwidth efficiency product. And so it's not always easy to measure the efficiency of small antennas, but you can do it in terms of signal-to-noise ratio. So Sussman-Fort shows improvement of 20 dB or so over relatively broad bandwidth, beating the Wheeler-Chu limit. And Steve Stearns, in another recent paper, shows also an improvement in noise floor compared to other methods of matching or other active antenna designs. This is one with an integrated amplifier. This is one of our results. We don't yet have measured data on these, but this is a small loop antenna. Loop antennas have an advantage compared to the short dipoles that you just saw. You can control the radiation resistance, the real part of the impedance, by the number of turns of the loop. So that gives you a little bit easier time in matching it. And taking the bare loop by itself that has a couple megahertz bandwidth, compare that to one that's matched with a negative inductor and also a small negative capacitor, and you're getting about 20 times the bandwidth. And that would be about 2 times the Wheeler-Chu limit. Remember, Wheeler-Chu limit is based on passive matching. So with these active structures, negative inductors or negative capacitors can only be implemented with active circuits. We can exceed that limit. Let's talk about another antenna application. This is parasitic arrays. You're all familiar with the concept of parasitic arrays. Many of you in the old days probably had one on the top of your roof. The Yagi-Uda antenna is the most classic example. So one element is fed, and the others are all either reflectors or directors. So they all scatter the radiation from the driven element with some phase, and that phase adds to produce a beam in the intended direction. Now, people have also made steerable versions of these, the so-called electronically steerable passive array radiator, where one element would be fed and all of the others would have some reactance attached to them. And you tune that reactance and you can steer the beam around. Same basic concept, but electrically steerable. The problem with these is if you look at where the radiation's going, that driven element radiates directly. All of the passive elements, the radiation has to hop over to that element, down the feed, off of that reactance, which you're tuning, come back up and reflect back or transmit back out. And sure, that can add in phase to produce some desired beam at exactly one frequency. But how could those paths possibly add up at all frequencies over a broad bandwidth? Well, if these were non-Foster circuits, in fact they can, think of a small shorted transmission line as similar to an inductance. Well, a negative inductance would look like a small shorted transmission line of negative length. So attach negative inductors or a combination negative inductors and capacitors, and you can get a beam or a null that is basically constant in angle over a broad range of frequencies. So this is, again, simulations. We're in the process of building these. But the basic idea is you can do pretty well if you use a negative L, negative C circuit, and you'll get that typical S curve that you'd have for a resonant circuit, but in this case it's inverted because they're negative. and you take the phase of the delay between the elements, add in the reflection phase from that non-Foster circuit, and you can get a phase that's basically flat with frequency, and you can change the slope of that. So this is for ideal antennas, not including any of the dispersion in the antenna itself. And then these plots are HFSS simulations of actual antenna elements loaded with ideal negative C's and negative L's. And you can see we're not getting the full 6-to-1 bandwidth, but we're getting a little better than 2-to-1 bandwidth. These curves for 3, 4, 5, and 6 gigahertz are relatively similar over most of the range. 6 gigahertz falls apart there as we steer the null to the opposite side. So we're currently in the process of building these circuits. As I'll show you at the end, we now have negative C's and negative L's, so our next step is put these all together with real antennas and then scale this up to larger arrays. So let's talk about another application. It could be an antenna application or it could be a cloaking application. Leaky wave antennas. So a leaky wave antenna is, instead of discrete antenna elements, you have a continuous structure, and a wave propagates along that structure and just gradually leaks out. There are a number of ways to build them. One of the most common ways is that waveguide structure supports a slow wave of some kind. This would be a number of possible dispersion curves. So a slow wave is below the light line. And then we use periodic scatterers to provide phase matching between that slow wave, this long wave vector, and the wave vector in free space corresponding to the angle we'd like to steer to. And the period of those scatterers then determines that radiation angle. Of course, this kg and k naught are changing with frequency. This period is fixed, so we get what we call beam squint, or the beam angle varies with frequency. It's a common feature or drawback of all leaky wave antennas. Some people use it for frequency steering. Of course, many people would like to have it be frequency independent. So another way you can do it is with a mode that's near cutoff. So then you can actually have what we call a fast wave. The phase velocity can be faster than the speed of light. Of course, you see that that's generally very dispersive also. So small changes in frequency will cause large changes in wave vector. So this turns out to still give you a lot of beam squint. Oh, thank you. So what we'd like to have is a fast wave structure where phase velocity is constant and greater than the speed of light over a broad range of frequencies. So the basic idea is build in negative capacitors that will counteract a portion of the dielectric constant. So you have an effective dielectric constant that's a function of both the real dielectric constant and this network of negative capacitors that you build in, and that would theoretically give you this fast wave behavior. So this is a simulation for waves propagating on a slab with epsilon less than 1, which is what we're creating here. And you can see you get constant beam angle with frequency. This is now a series of simulations for creating effectively the same structure with a series of negative capacitances. And you can see, again, for various steering angles, we get beam angle constant with frequency. This is over 10-to-1 bandwidth. So, of course, when we talk about superluminal propagation, everybody's worried about causality. So this chart is intended to show you there's really nothing to be afraid of. Superluminal propagation has been shown in lots of structures, optical frequencies, microwave frequencies. Doesn't necessarily violate causality. Causality says you can't send information faster than the speed of light. The phase velocity really just tells you what is the spacing between the wave crests on that waveguide. And the group velocity is just how that varies with frequency. So we can set up something that supports superluminal propagation. We still can't send a pulse through that faster than the speed of light. So there will be bandwidth limitations related to how those pulses line up. The next step in this, of course, is extend it to 2D structures and to take some of the narrowband cloaking structures that we've shown in the past with passive structures, and you could think of the general approach to cloaking as something that absorbs a wave on one side and then re-radiates it on the other side. So with these leaky wave antennas, you could build things like that. So now let's talk about the non-Foster circuits and how we build them. Well, in fact, they've been around for many decades. In fact, the original one was used in the telephone system, this effectively creates a negative resistor that balances the resistance of the telephone lines, and it gives you essentially a bidirectional amplifier. This turns out to be a very simple way of making a telephone repeater. This is the most well-known circuit, very simple, just 2 transistors, and Linville, this is often attributed to Linville, although if you look into the details of this repeater, his circuit is essentially the same. His is really just the first transistor implementation of it. The easiest way to understand it is the voltages in these 2 transistors pass through the base emitter junction. So that's a constant voltage. So if you were to trace sort of the path of the voltage drops, it goes around through this way along the red curve, passes through this model impedance, and comes back down through this base emitter junction. The current, of course, flows this way through the collector emitter and passes around that impedance this way. So notice those are going in opposite directions, so you get a pi phase shift between the voltage to current ratio. So basically, this impedance appears as the negative of that impedance out there. Now, we tried simulating many of these structures, built them, and they looked nothing like our simulations. So what was happening, it turns out that even though it's a simple circuit with just 2 transistors, it's not that easy to implement. All of the parasitics of the devices, the passives that you include, in fact, even the circuit board itself, they all play a role. And so to get good match between simulations and measurements, even at UHF frequencies, you have to include full EM simulations of the circuit board. Of course, ultimately, we'd like to go to an ASIC where all those parasitics are much, much smaller. But for now, we're building these what you might call Radio Shack style. So you'll notice in the literature a dozen or so different non-Foster circuits. In fact, we've shown that all of them essentially are the same circuit, and the impedance seen at one port is a ratio of the impedances seen at the other ports. So those can be anything you want, resistors, capacitors, or inductors. So you can make negative capacitors, negative inductors. In fact, you can even make a negative inductor out of a capacitor by inverting a capacitor if you'd like to. Of course, we'd prefer not to use inductors. So this is some of our preliminary measurements. After including full-wave simulations of the circuit board, we're actually getting a very good match. This is about minus 30 nanohenries down in the UHF range. I mentioned that we're using just discrete components, and that gets us up to about 200 megahertz or so. People have shown non-Foster circuits using ASICs up into the gigahertz range, so this can be practical for real wireless applications at some point. And notice here we're going in the counterclockwise direction. Oops, that's showing the wrong direction. That arrow should be going this way, in the counterclockwise direction around the Smith chart. This is a tunable negative inductor by inverting a varactor. You can see we can tune from about minus 30 to minus 65 nanohenries. We should be able to get a better tuning ratio. It's only 2 to 1 because of the other parasitics around that varactor, but we think we can play with the other impedances to improve that. And we've also started simulating floating versions. This is all measured results, but we've started simulating floating versions also, which are necessary if you'd like a series negative inductor. And this is our first negative capacitor measurement. So this is, so we see an impedance at the input, which is the ratio of these impedances, and if one of those is a varactor, then again, it's tunable, and we can get about minus 7 to minus 12 or so picofarads by tuning that varactor. So this is where we are with the research at this point. We have a lot of interesting applications. Small antennas, broadband, parasitic arrays with much greater bandwidth than you could get with simple passive structures. Interesting ideas like superluminal propagation, broadband leaky wave antennas, possible cloaking structures. We now also have measured results on the circuits, and so our next step is put those together. I didn't get into all of the details or all of the issues with stability and practical issues with implementing these. And of course, those are going to come up as we start combining them with EM structures. But I think we're making good progress. And if you were to look into the future, I've just shown you a couple of examples, but everything that people have tried to make with metamaterials so far potentially could be enhanced by including active electronics. So if you really wanted to make a broadband negative mu material or negative index material or things like that, potentially this approach could do that. I haven't gotten into some of the other things we're working on, like including nonlinearities in these structures, but that's a topic that I could talk about afterwards if you're interested.
Questions? You want to ask the first one?
Yeah, I think I talked loud. Negative, actively synthesized negative impedances are actually very commonly used in ASICs.
Sure.
One of the problems that I think you didn't mention was the extra thermal noise that you get from these structures, and very often that sort of negates their benefit. How is that in antennas? And in your
Right, so the same issue is true in antennas, and that's why when we want to show an improvement in performance, we can't just show a match having a broader bandwidth. We have to show a real improvement in signal to noise or a real reduction in noise floor. And in fact, a couple of people have shown that so far. There's plenty of other issues that I didn't get into as well. I mean, there's a whole talk on, I've shown the good side. There's a whole talk on the difficulties of these. Stability is one of them. Nonlinearity is one of them if you want to use it for transmit. And all of these things come up. But like I like to tell people, this first bullet here, if all we're going to do is just rearrange metals and dielectrics, we're not going to do any better than we can do today. So I think including active electronics gives us a way around that. John?
Thank you. I was very interested to see on your last slide the connection with possible negative refraction, negative epsilon, negative mu. There is another way connected to your thinking of producing these without having a passive material, and that's to use time reversal, because a time reverse signal looks as though it's propagating in a negative medium, but of course to create it you have to have an active nonlinear process, just as you say. Sure.
Mm-hmm. Right. In fact, that's a good point, and one thing I didn't mention at the end, I assume you're talking about optical approaches. I think many of these things could be applied to optical applications also. You know, these transistors are just providing gain, and we can do whatever we want with that gain. Of course, you have gain materials at optical frequencies also.
Well, actually, we've had some excellent questions. I just wanted to comment how remarkable it is that it's taken so long that we put active elements into antennas. And it turns out, up until this point, they've been totally passive, and it's a very big industry now. You know, but this year we're beginning to see changes. We're seeing active elements included in antennas for the first time, including by the company I founded, CITRIS. They just brought out their first active antenna product.
Yeah, it's amazing. You know, you'd think that the Wheeler-Chu limit was from the 40s, right? And we've had these circuits since about the same time with the telephone system. And so why has it taken us so long? I don't know. It's an interesting issue.
Any other comments? So we are a little bit behind. So let's thank our speaker first.
Thank you.